Okay, good afternoon, 61C. Good afternoon. Yeah, glorious spring day. Spring's here again, sunny California. And you're inside learning about caches. Okay, but it's such a fun thing, right? Caches part 2. So I realized last time there may have been a lot of confusion about ways and sets, and so I'm going to spend some time today reviewing and going back over that, trying to explain it a bit more clearly. But just to remind you, we're in this big system stack, we're in the cache memory level, right in the heart of each processor, how it talks to memory. So just to quickly review what we went over last time, we talked about the principle of locality, and this is a property we observe about programs that pretty much every single program that's written has some form of temporal locality, some form of spatial locality in the accesses they make, both for instruction fetches and for data accesses. And that's really the key insight that enables us to build memory hierarchies that exploit that locality and make it possible to build reasonably cheap computers that work really fast with really large memories. So what is a cache? Well, it's a small memory that you put in between a processor and a bigger memory, and its job is to keep a small subset of the data in the main memory, but keep it close to the processor so it can be quickly accessed. And we rely on locality to give us this property that most of the time you hope to find things in the cache, and so it seems as if your memory is running very fast because it's kind of cheating using this cache to return things more quickly without going all the way out to the big main memory. So the trick is, how do we build in hardware some structure that is fast to access, that can search and find whether a given address the processor is trying to access is in the cache or not? And we went through some of the cache structures. We'll go through that again this time. Direct map, two-way associative, fully associative. These are different design points, cache organizations, and they have different trade-offs in terms of, how often will you get a hit or a miss, and how fast is it to access the cache. And today we'll talk about those design trade-offs as well. One of the detail we talked about in the cache you have the data, but you also need this tag, which tells you which address that data is a copy of. And also, in addition to that, we talked about a valid bit that simply tells you, is this entry a valid entry, or is it just garbage that was there maybe from the last time you powered on? Well, I didn't summarize here, but is in the last bullet. We have to also worry about writes. So reads are kind of easy to think about. You're just loading stuff from memory. But an important thing a processor does is change what's in memory, and it has to write data back. And we talked about these two fundamental design style choices in handling writes. One is a write-through, and one is a write-back. And in the case of a write-back cache, you only update memory when a cache line is evicted from the cache. And in order to know whether you need to update memory, we had this optimization we call the dirty bit that was kept alongside each cache line. So you have the valid bit and the dirty bit in a write-back cache, as well as the tag associated with the data that's held in the cache. So that's what we covered last time. Let's go back over it again. So here's the processor, here's the memory. We showed this picture before. The cache just really sits in between the two and intercepts those requests and tries to service them more quickly than going all the way out to main memory. So when it intercepts those addresses, remember that the software running on the processor, and maybe even the processor itself, doesn't know there's a cache there. It just sends out the full address that expects to get the data back from the full memory. But internally, the cache controller is looking at the address that comes in, those 32 bits that come in, and is splitting it up into these fields internally so that it can search in the cache to find where data is. And so there's these three major components of the address, how it gets split up into these three fields: the tag, the index, and the offset. So starting from the other side, the offset is simply each entry in the cache has a certain size. Is it one word of 4 bytes? Is it many words, 16 bytes, 32 bytes? It's some power of 2 number of bytes. And log 2 of that number of bytes is how many bits you need to select a byte within that block. Remember, the processor can do byte access as well as word access. So that full 32-bit address, the bottom bits tell you which byte you're touching. And then also which word and which byte within that block. And that's all in this block offset at the bottom. And that doesn't really play much role in the cache access itself. It's just once you find the block is in the cache, it figures out which piece of that block you want to send back to the processor, right? So that's the role of the offset. The index, however, the set index, this field is used to tell you in which subset of the cache might you find this data, right? So you divide the cache into sets to reduce hardware cost, right? So for a given size cache, the more sets you have, the fewer ways are in each set, and so the fewer places you have to search in parallel to find a match. And the extreme case is the direct map cache, where every set only has one way. And so there's only one possible place something with that set index could live, and so there's only one tag you have to check. And so the final field is the tag, which are the bits of the address you kind of haven't already used up in locating data within the cache. And so this is where you may have different possibilities for what lives in a given way. And so you need to check, the tag has to be this big in order to distinguish different memory addresses that might live in the same set within the cache, okay? So tag, index, offset are the three components. And so playing around, and remember, this is invisible from the processor side. It just sends the full 32-bit address over. It's the cache's job to break this up and use this to index into the cache. And also the cache has to work as if the cache was not there, right? Functionally, it has to return the data, accept writes, just the same way main memory did. So all this should be invisible to software running on the processor, that this is going on. So let's review the direct map cache structure. So we'll start with a simple design that has a one-word block, i.e. each entry in the cache has space for 4 bytes of data. And each of those blocks of data has an associated tag. Okay, and the size of that tag will be dependent on index field and offset field. So in the case of this cache, there's only 2 bits of offset, which byte within those 4 bytes you're interested in, or the start address of the unit you're interested in. The next 10 bits in this case are going to be the set index. So this cache has 1K sets, 2 to the 10 sets, 1024 different sets. And so the next 10 bits are used to tell you which set the address will be mapped to. And finally, the tag is the thing you need to check to see if the current resident of that set matches with your current access. So the way you proceed, the cache controller receives the address from the CPU. It just grabs these bits from the address and feeds those to a RAM that's holding. So this is just the tags invalid are also just memory bits, just held in a memory structure in the hardware. And you feed these index bits in as the address of this memory. So from 0 through 1024 are possible addresses into the memory, and you read out the tag entry at that index, as well as this 1-bit valid indicator, just to make sure it's a valid entry. You then read out, in this case, there's 20 bits of tag. There was 2 bits for the offset, 10 bits for the index. Out of 32 bits, that leaves 20 bits for the tag. So there's 20 bits of tag. You read 20 bits of tag out of here. You compare them with the upper bits of the address. And then you have to also check that the valid bit is set, so that then you can say, oh, I got a hit in the cache, i.e. this address matched in the cache. Okay, so you know you got a hit. You can then forward this read data from the cache to the processor instead of going to main memory. And that's the good case, right? You got a hit, it's in the cache, things run fast. Right, remember this structure in this case is only 1K entries, each with 4 bytes. So this is a 4 kilobyte cache, a 4 kilobyte direct map cache, right? And so this is much, much, much smaller memory than, say, a 4 gigabyte DRAM main memory you'd have in your system, right? So 4 kilobytes is how many times smaller than 4 gigabytes? $4K versus 4 gig. How big a difference? What's the ratio of sizes? 1 million, right. So 4K is 1 million times smaller than 4 gig. So this is a small cache. But surprisingly, even a 4K cache, you may get something like a 90-95% hit rate in just a 4K cache out of programs that are running in 4 gigabytes, right? And that's why it's such a powerful idea that a small, fast memory can give the illusion of having a big, fast memory, right? Or a big, not so fast, not so bad memory. Okay, so this is only for 1 million times smaller than all of main memory. That gives you some more insight into why it can be so fast. It's so much smaller. It's 1 million times smaller than main memory. Right, it's a tiny circuit. So introduce some cache terms. You've seen enough cache stuff to get these terms now, I think. So a hit rate is the fraction of accesses that hit in the cache. So, and this is the fraction of load and store instructions or instruction fetches that actually hit in the cache. So it's the ratio of number of hits divided by number of total accesses of whatever kind. Right? That's the hit rate. So the miss rate is just the inverse of that. It's just the opposite. 1 minus the hit rate. It's what fraction of accesses missed in the cache out of all the accesses made to that cache. The term miss penalty is used for the time it takes to service a miss. So once I get the good case is the hit. I go to the cache, it returns data in a cycle. I'm good, I'm happy. But it will miss occasionally. And when it misses, you have to wait to reload from the outer levels of the memory hierarchy. And so that time we call the miss penalty. And the simple processor, you're going to sit and wait for that data to show up. And in modern processors, you may be waiting for the equivalent of 1,000 instruction times. You're sitting there twiddling your thumbs, thinking there's 1,000 things I could do, but I'm just waiting on that data coming back from main memory. Another thing, we focused on misses here, but another important thing is the cache is a circuit structure that you're going to build inside the core of your processor. We store it in the pipeline, the instruction cache, the data cache in our simple pipeline. And it's going to be one of the critical path components in that processor. So the size of the cache has to be carefully tuned such that it doesn't impact the cycle time of the processor. So we worry about what we call the hit time of the cache, which is the time in nanoseconds or picoseconds in seconds to access the cache. Yep. The instruction, well, we definitely usually have a separate instruction cache separate from a data cache. And so I didn't quite understand the question. Right. Well, I'm not sure the difference between a separate data cache and a separate instruction cache. Is that what you're saying? Or, yeah, that's usually what you have. So one reason to have two caches is that you could access them in parallel. So I can do an instruction fetch access in the instruction fetch stage of my pipeline in parallel with doing a data cache access in the data cache stage of my data memory stage of my pipeline. And so I won't have a structural hazard. But those two caches will then be backed up. They'll both refill from the outer level memory, which is usually unified after that. But yes, you often have a specialized instruction cache and data cache. Another reason to have two caches is the two streams won't interfere with each other. So your data accesses won't kick out your instructions and vice versa. Okay, but this other term we're talking about is hit time, which is the circuit delay to get through the cache and return the data in the case that it's a hit. And in our simple processors, we'll keep that down to less than 1 clock cycle because it's often the cycle limiting path in a simple processor. Now the miss time is usually, in terms of this miss penalty, is usually many clock cycles. So we usually give the miss penalty in terms of clock cycles, the hit time in terms of nanoseconds. So one other thing you'll see on the slides, maybe we use this already without introducing this, we use a $ as shorthand for cache. Right, so dollar cache is a bad pun, right? And it was actually invented here at Berkeley, this shorthand. So it's a Berkeley innovation, the use of the $ for cache. I think it was either Randy Katz, Dave Patterson, or maybe Carlos Icahn came up with this. So you can blame them for the bad pun. Anyway, it's a convenient abbreviation. All right, so when thinking about the performance of a cache, there's this phrase we use, the average memory access time, or AMAT. And you hear a lot about this. It's an easy thing to ask quiz questions about. So average memory access time is the average time to access memory, considering both the hits and misses in a cache. So think about, we've talked so far, in a good case, when you get a cache hit, things are fast. When you get a cache miss, things are slow. a useful number to know is, on average, how long does it take to access memory, including both the hit cases and the miss cases. And so a simple formula here is, it's basically the average memory access time is the time for a hit plus the miss rate times the miss penalty. So remember, the hit time is given as in seconds, nanoseconds, picoseconds, as a unit of time. The miss penalty is usually given in terms of clock cycles, and so you'll have to multiply that by the clock cycle time to get the time penalty in time, and then you multiply by the miss rate to how often do you incur that miss penalty, right? So the miss rate says how often do you get that. Now notice the way we define this. The miss penalty is added to the hit time, right? So when we access the cache, almost all systems will look in the cache first to see if there's a hit, and only if there's a miss go out to main memory. So the miss penalty is added on top of the hit time, right? So you have the hit time is always there. Every access you're going to pay that hit time. And then only if you detect there's a miss by not getting a hit, will you then actually go to do the miss and incur the miss penalty. What would happen if you tried to do an alternative scheme would be what? How could you imagine doing better than this scheme? Yep.
You could do both simultaneously, then you have a box at the end, select the output.
Right, exactly. So you might imagine doing something like, I don't know if I'm going to get a hit, and instead of waiting to find out I've got a miss, I may as well get going straight away. I'll just go prefetch the data from memory because I don't know if I'm going to get a hit or not. So what might be a problem with doing that? Anybody can think of an issue? Yep. Yeah, one thing, you're going to have to keep track of all those requests you have. If memory is 400 cycles away, you may have 400 speculative memory operations in flight, and some of them you'll want when they come back, and some of them you won't want because you've already hit in the cache. You have to keep track of them all. That's one cost. What's another problem with doing this? Yep.
If that value's been updated in some other cache that hasn't been put back to main memory, it could be a stale value if you have to fetch it from it.
So a concern here is, are we going to get the correct values from memory if we do this? Well, that's actually a concern even if you don't do the speculative fetch, and we'll talk a little about that later, about the cache coherence problem. If you have multiple caches, you're trying to give a consistent view of memory over. So that would be a problem even if you didn't do the speculation in parallel. But what's the real problem with, on every memory access, going to main memory as well? Why do we put a cache there in the first place? The main memory's slow, right? So it cannot support you sending this constant stream. If you imagine this, it'd have to run at the same bandwidth as this tiny structure that's 1 million times smaller. You can cycle that a lot faster than you can this big structure that's 1 million times bigger, right? So you cannot just keep sending all those requests out to main memory. The bandwidth demand will be tremendous out of the main memory. You wouldn't be able to support it at reasonable power. If nothing else, the power to send signals all that way and get them back again at that rate would kill you. So it's really a bad idea in terms of just the power and the bandwidth you need to support from main memory. Now, having said that, there's an anecdote I can tell you about a certain microprocessor. This was a digital alpha, DEC alpha. This is a RISC processor from the early 90s, 21164. And they had a level 1 and level 2 cache on chip. And they built a level 3 cache off chip using commercial static RAM parts, static memory parts that were faster than DRAM. And they built a level 3 cache from this. And they did this trick of, they got missed in L1. It wasn't on every access. When they missed in L1, they went to L2. They also went out to L3. And so they would actually speculate they'd missed in L2 and go get started on the L3 requests. And they found that their machines didn't work with certain parts from certain manufacturers, these off-chip memory chips. And the reason was that they were driving these addresses far above the spec that the designers of the SRAM ever intended. And these things just wouldn't work at that speed. And it was a spec that the SRAM guys didn't actually build into the data sheet. They didn't think of it as a thing anybody would ever do, and these guys at DEC tried to do it, build a system around it, and some parts from some manufacturers worked, some parts didn't. And luckily, they put a disable in the chip so they could turn off this feature. But if you think about it, the one reason you put the cache in there is the outer levels of memory are slower, they have less bandwidth, higher latency, so you don't want to speculate. And also, it's not going to buy you that much, because most of the time you get a hit. You want to design the cache so most of the time you're getting a hit. And how much time do you save by starting it in parallel? Yep. Right, you just save like one cycle. And if memory's like 400 cycles away, it's like, whoop-de-doo, I got it in, 400 instead of 401 cycles. It's not going to make a big difference to your system, and you're going to waste a lot of power doing those accesses, right? So it's not a good thing to do. So, simple model. Time for a hit, look in the cache first, see if I get a hit or a miss. Then, only after that, send the miss out to memory. So it's time for a hit, plus the miss rate times the miss penalty. Clicker time. So this is a pretty simple question, just to confirm you've got AMAT down. Okay, let's take a look. So, okay, we have a clear leader, but a bunch of people think A is the answer. I think I'll give you just 1 minute to talk to your neighbors. Okay. Quick 5 seconds, get your vote in. Okay. Okay, we seem to have violent agreement here, and that is the right answer. So let's just go over that. So the 200 picosecond clock, a miss penalty of 50 clock cycles, a miss rate of 0.02 misses per instruction, and a cache hit time of 1 clock cycle. What does aim at? So time for a hit is 1 clock cycle of 200 picoseconds. So if there's any miss penalty, it can't be A, right? A is less than or equal to a single clock cycle. It's going to be 1 plus something. And 0.02 is a 50th, right? So a 50th of instructions get a miss. The penalty is 50 cycles, so on average, every instruction has 1 extra cycle of memory access time. So the answer is B, 400 picoseconds, right? And that's how you get AMAT. Notice here, like, there's only a few percent misses, but because the penalty is so high, you've basically doubled your execution time, right? Every instruction takes twice as long as you thought it did, even though most of the instructions are cache hits, right? The ones that miss take a long time to come back, and that has a big effect on your system performance. Okay, now let's start taking a look at cache design and look at some, how does the cache operate when code runs on it? And we'll look at this particular pathological case that shows up on a direct map cache. So this direct map cache we're going to look at has just 4 words in 4 sets. So there are 4 single word lines. So it only has 4 sets. Each set has 1 way because it's direct mapped. And that entry just has 4 bytes of data, a single word. Right, very small cache, only 16 bytes of data. And then let's look at what happens when the CPU sends this string of memory addresses to the cache. So this is looking at coming out of the CPU address pins, what memory addresses is it accessing over time. Right, we're going to look at the dynamic behavior of this cache. So, and these are of, I should have said, these are of words and not of bytes. Yeah, I should have left that on the slide. So it's actually word 0, word 4, word 0, word 4. So accessing word 0 here, well, first of all, the cache is empty. Let's assume that. Everything's invalid. So you're going to get a miss, and then you're going to replace the first set is going to hold the memory location, the word at memory location 0, right? The 0th word. Okay, then you do word address 4. Now, word address 4, 0, 1, 2, 3, 4, wraps back around to the same set, right? So remember the way the direct map cache works, the set index, it's just a modulo counter in effect. As you step through memory, you just stripe over the different sets. Okay, so word address 4 is also in set 0. You look in the cache and you see, well, this holds 0 right now, so it doesn't have my location 4, so that's a miss. So I'm going to wipe that out and replace it now with the correct entry, right? So the tag field is now, so 2 bits are used for the set index, and these remaining 2 bits in here are actually the tag, right, a 2-bit tag. So this guy now writes in 4, then you come back and you do 0 next, and 0 looks in the same set, the same way, same entry, same tag, and finds, look, oh, this doesn't hold 0. I need to kick that out. So I get a miss, and I kick it out, and I write 0 in there, and so on, right? So you have this alternating stream of memory addresses that all map to the same set in a direct map cache. There's only 1 entry in every set in a direct map cache. There can only be 1 memory address there. And so these 2 guys just ping pong and alternate. And so every single access is going to get a miss. You're going to get 100% miss rate with this reference pattern. Okay? So this is what we call a conflict miss. So these 2 locations in memory map to the same set in the cache, and only one of them can be in the cache at any time. And so if you alternate between these 2 addresses, you're going to get this ping pong behavior where they kick each other out all the time. And this is a pretty bad pathology. It's going to give you pretty poor performance when this shows up, because you're not getting any benefit from the cache now. It's actually just getting in the way and making things slower than if you didn't have the cache, right? Because you're not getting any cache hits. So to help avoid things, we call those conflict misses, To help avoid those, we come up with better structures for the cache. The direct map cache was the first structure people built for caches. And from when it was first proposed and invented, it very quickly was adopted. It was like one of the easiest, best, quickest ways to speed up machines because it was invisible to software, and even you could hide it from the hardware of the processor even, and it was very easy to add to machines and gave a big speed up. So those initial caches were very quickly adopted and made it into commercial use very quickly. And along the way, people figured out many different ways of building them, and we'll talk about some of those ways today. And one design choice is how many sets you have and how many ways in each set. That's like one of the big design spaces. So direct map cache is what we focused on so far. Basically, every data entry is its own set. And so when you search in the direct map cache, you just look in one place. You go directly from the memory address to one location in the cache. You look at one tag to determine if your entry's there. If you have a fully associative cache, that's the other extreme. In a fully associative cache, when you look in the cache, you have to check every single tag in the cache in parallel, right? And that's shown by all these arrows here. So I look across all these tags to find this entry 12, and I have to look at all of them. And in between, you have what we call a set associative cache, where each set is associative, but the set index is used to guide you to just a few of the ways within that one set, within which you have to search. So this cache is a two-way set associative because every time you get an address to the CPU, you just look in two places, these two ways within one set. So the set has two ways, colored white and blue here, and you just have to look in these two ways. If you had a different memory address, it may point you at set 2, then you would just look at these two tags, and so on. So the set index selects the set. Within the set, there can be more ways. You have to search all the ways within a set in parallel to look for a match. Right, so that's the idea of a set associative cache. Question?
For searching for the index, or when you get the index, do you have to search for the index, or how does it automatically just know?
The index is just, when you build the hardware, you've already designed that the index is these bits from the address. So literally just grab those wires that the CPU is sending you and say, well, those 10 bits are my set index. And I'll just feed those into as the address port of my memory that holds the tags. And then I'll get the tags out sometime later. So you don't have to do any search. You just know it's hardwired in. Bits, in our earlier example, bit 2 to bit 11, those bits were the set index. So I just connect wires to those bits coming from the CPU and wire those into my address decoder for the memory, right? So this is, all these hardware cache parameters are set at design time, and you hardwire the cache to support one organization. But architects spend a lot of time figuring out which cache organization they're going to use in this next chip because it is such an important part of performance and energy consumption. So, this is just some text. So direct map placement, you can think of this as taking the modulus, take the memory address mod 8, and that tells you which set you're in. And here it's memory address mod 4. That just means there's 2 bits of the address you're using to tell the set. In this case, there's no... One thing, in a fully associative cache, you don't need a set index. There is no set index bits. You only have one set. So you just have to search for all the tag bits in all the ways. Yep.
Is there some advantage to any one of these guys in a particular scenario?
Yeah, we'll go through in why you would pick one or the other as we go through the rest of the lecture. It's about that exactly, about the trade-offs. So all of these designs are used in different places. So none of them is definitively superior to the other. Depends on your design constraints, where you would use one or the other. All right, so all of these are used in practice. Okay, let's just look at the set associative cache just to show how it solves that conflict problem. So this is drawn with the ways above the line, way 0 above the line, way 1 below the line, and then the sets of these two colors, black and green or blue and green. And this is that earlier example we had last time of a 6-bit memory space where 2 bits tell you the byte within the block. The next 2 bits the next 1 bit tells you which set it is, black or green, and then the high 3 bits are in the tag. Remember last time when we had the direct map cache version of this, there were 2 bits for set index because we had 4 sets. Now we've increased the associativity, made it 2-way. We'd lose one of the set index bits, which grows the tag by 1. So now the tag is 3 bits. Last time it was 2 bits. Okay. And now notice that this one location in main memory, this one memory address, can either be in this place, in set 0, way 0, or it can be in this place, set 0, way 1. This memory block can either live here or live here. Same as this green block here can either live here or live here. The black and green say which set it can live in, but the high order tag bits, you're going to have to do a comparison to see which way it actually lives in, right? Okay. Right, so this is just highlighting all the memory addresses that can live in the blue blocks. So in these two locations, any of these memory addresses can live in these two locations, and any two different of those memory locations can live in those two ways, right? So now let's go back to this little example again, these word addresses again. So now 0 is a miss, and you place it in way 0 of set 0. And when you get to the reference to word 4, you find, well, I don't have it in the cache, but I can place it in way 1 of set 0. And so now those two locations can coexist in the cache at the same time, right? They have the same set index, but that set now has two ways, so two places to keep things, right? So we can hold on to both of them even though they have the same set index. And so from this point onwards, you know, things are good. You're getting hits, right? So you get the initial two misses to load up the cache, but after that, you can access both those locations without getting any cache misses. All right, so now we've removed the conflict misses by adding some associativity to the cache design, right? By making it set associative instead of just direct mapped. So there is this design space. This is one thing you should get across, important thing to get across today. If you take, say your budget in terms of cache area is mostly dominated by how much data are you storing in the cache. Most of the cache is these data bits. So say I tell you here, you can have 8 blocks worth of data storage in your cache. What are all the different ways of arranging that? Well, this kind of walks through that. You could build a direct map cache. It would have 8 sets, 1 way per set, and that's how you use your 8 blocks, right? 8 blocks of data. Or you could take your 8 blocks and make them fully associative, right? So now I have 8 blocks of data in the cache, all fully associative. In this case, I'm going to search all the tags in parallel on every access. Or I can make it 2-way set associative. Now there's 2 blocks in each set for the 2 ways, and now I have 4 sets, right? Or I could make it 4-way set associative. I have 4 blocks in each set, and now I only have 2 sets. So you have this complete continuum between direct mapped and fully associative, depending on sort of how you shuffle things between sets and ways. All right, so that's the design space you have. But all of these have, notice they all have the same amount of data, and they all have the same number of tags, though the actual size of the tags will change, right? If you have a direct map cache, you have a smaller tag because more of the bits have been taken up in the set index. If you have a fully associative cache, there are no bits used up for the set index, so your tag is bigger, right? Okay, so we'll repeat that again a little bit. So let's just look how you would physically build this. What would the hardware circuit look like? Well, building, say, a 4-way set associative cache is really easy. What you do is you take the direct map cache circuit we had before and just repeat it 4 times. So in each direct map cache, you're going to do a lookup at the same index. So one of your direct map caches acts as way 0, one is way 1, one is way 2, one is way 3. So you take the same bits out and you feed them in parallel to all 4 of these subcaches. Each subcache reads out a tag and a data and locally does a compare, right? And then only one of them should hit, if any of them hit, and that's the one whose data you need. So at that point, you then see which one has a match and mucks out the data from that cache back to the processor, right? So you have a big Did anybody? So I OR together all the hit signals. Did anybody hit? If anybody hit, then there was a cache hit. I then use these hit signals to drive a MUX that picks the correct Waze data to feed back to the CPU. Right. Now, they may all miss, in which case you have to go to memory, bring it back in again. Right. But you can just see here that if you have the direct map cache building block, it's very easy to extend it to make it set associative. Right. And if you had the same capacity, obviously each of these would be smaller. So in this case, we've divided it into 4. So our initial 1K direct map cache now has only 256 sets, but 4 ways. So 4 copies of that. All right. So this is a simple way to build a 4-way set associative cache. Question?
How do you ensure that you only write to one way when you're writing data?
So a good question. How do you know there's only one of them at a time has a given address, right? Well, the answer is your hardware has to make sure not to, well, you first search before you put anything in there. If it's already in there, you don't need to do anything. You just use that entry that's already in there. If there's a miss, then you know it's not anywhere. And so it's okay to evict one of the entries and write your new entry in there. So the hardware maintains that invariant that at most one of those ways can have a given memory address. Or memory address can only appear once in the cache. Right? So your hardware is handling the refill too, so it knows not to do. Just don't do that is kind of the answer. Yes, it would break the circuit if you had 2 places had the same address. That would be bad. So getting back to this trade-off between associativity and set index size. So actually I've now shown you more clearly this offset is really broken into a byte offset and a word offset. But really you can just think of this as an offset. Which bytes am I interested in the cache entry? For a fixed size cache, this is important. When the cache is fixed in size, every time you increase the associativity by a factor of 2, so you double the number of ways, you've kind of halved each of those subcaches, right? You double the number of ways by taking each direct map cache, breaking it in 2, and then searching the 2 halves in parallel. Every time you do that, you halve the number of sets. Halve the number of sets means reduce the set index. So this gets smaller by 1 bit, and the tag gets larger by 1 bit. So the more associative your cache is, the larger your tags have to be. Right. It just follows from the fact there's more freedom in where a given entry could be in the cache. And so you've changed from, searching based on the address to tell you exactly where it is to searching based on looking at the content to see where it is. Okay, so increasing associativity moves that to the left. And if you go all the way, so there's no index, then you're fully associative. You just search for the tag everywhere. If you go all the way the other way, then there's no associativity. You have enough index bits that every line is in its own set. That's a direct map cache. Okay, so set associative caches, what are the costs? Well, you have the storage is about the same. The tags are a bit bigger, but only by a bit or 2, right? But the big cost is in the extra comparators, so I have to do more compares, and that adds delay as well as area. A bigger problem is the MUX delay. So I do not know, if I go back to the circuit, I don't know where the data is coming from until I do the tag compare, right? So I don't know which piece of data the processors use until I do the tag compare. In a direct map cache, I always know where the data is coming from because there's only one place it could be. It might not be a hit, but at least I know if it's a hit, that's where it's going to be. In the case of an associative cache, though, even if it's a hit, I have to wait to figure out which way got a hit before I can start using the data. So there's an additional delay through this select logic before you can start using the data, right? So a lot of processors will guess that there was a hit and just use the data and keep going. And you can't do that here. You have to wait to figure out which way got the hit before you can start using the data. So associative caches are slower for that reason. So now, another interesting thing is, with a direct map cache, you don't have to worry about what's called the replacement policy, right? Who do I evict when I get a miss? Because in normal use, the cache is always full, right? So whenever I get a miss, I have to kick something that seems to be useful out of the cache. And who do I kick out of the cache? So that's the replacement policy. In a direct map cache, it's really easy, because there's only one place anything can live. So whatever's in that slot, in that set, has to go. Every set only has one way. There's only one place the new item can live. You have to kick out whatever was in there previously. Once you get to 2-way or more, you now have a choice, because there's 2 or more places the new item can live. Which one should I kick out? Well, one of the commonly used policies is called least recently used. And this idea is, well, if there's 2 items sitting in a 2-way associative cache, and I have a new item coming in, I should kick out the one that I haven't used in the longest time, right? Which one did I use more recently? Kick out the other guy, right? Because now, why is that? Why does that make sense? Why should you kick out the one you've accessed furthest in the past? Yep. Say again? You're less likely to reuse it because you haven't used it in a while. And what's the principle? Temporal locality, right. So you're right. So the intuition is, well, I haven't used it in a while. I used this guy more recently. So temporal locality tells you if I've used something recently, it's more likely I use that than something I accessed a longer time ago, right? So it's more likely the thing you've touched more recently is the thing that you'll use. Now, it turns out for a 2-way set associative cache, keeping track of this is really easy. You just have 1 bit. This is an extra bit of state in the cache that tells you in each set which of the 2 ways I touched most recently. So every time I access the cache on a hit as well as a miss, every hit, I say which way got the hit, and then set the bit to point to that way, way 0 or way 1. So that 1 bit records, was it way 0 or was it way 1? And then when I get a miss, I kick out the other guy, right? So that's very easy, and you can do perfectly accurate least recently used. It gets much harder as you go beyond 2. And as a result, people have come up with different replacement policies, right? If you think about it, if I have 4 ways, every time I, pick up one most recently, I kind of need to pull it out of where it is and put it on top of a little stack. Imagine a stack of plates, right? Oh, I access the 3rd plate. Okay, that's the most recent. I'll put that on top. And you keep going like that. And when you get a miss, you kick out whoever's at the bottom of the stack of plates, right? Because that's the least recently accessed plate in that example, right? Doing that in hardware gets complicated exactly as you get beyond 2 entries. You can do it exactly for 2, and people do. But beyond that, people use some approximation. One approximation is random, right? When I get a miss, just kick something out. Just pick one at random and kick it out. How well do you think that works? Pretty good. Yeah, actually it works okay. It's not terrible. It works okay because, well, for one thing, if you get more than 2 ways, you've got a, diminishing chance of kicking out the wrong guy. It only really matters if you kick out the thing you're about to use next. You kick out something that was, not that important. The chance of kicking out something important are smaller the more ways you have. Another thing is if you guess wrong, all that happens is you'll miss on you'll kick something out you shouldn't have kicked out. Then you'll access again, you'll bring it back in the cache and kick something else out. And it'll be back in the cache again, right? So it'll soon come back into the cache. Another advantage of random is if you have some patterns in your code, like some kind of loop structure, random will tend to avoid any pathological case, whereas anything that's more deterministic will tend to, you might get these weird beating patterns where it does exactly the wrong thing for your memory reference pattern. And those are great things we give you on quizzes, is here's a reference stream. Tell me the reference stream that gives you the worst case in this kind of cache. But random avoids that by doing that. However, it's very difficult for programmers to tune their code when they have random replacement. So performance programmers hate this. So, okay.
Could you have like a regular, let's say, like system that you throw in random elements every now and then, like shake it up?
Yeah, people propose many, many different proposals. Do some directed and some random. Yes, people propose many things. In practice, most systems today use pretty simple replacement policies. So we talked about the simple 2-way one. You just need 1 bit. That's easy. People often do approximations of LRU. So one common one, if you have a large number of ways, is what's really a not most recently used. So the idea is, whatever you do, don't kick out the thing I did use most recently, and everything else is considered less recently used than the most recently used. So find something that's not the most recently used and kick it out. And the way you do that is you have a little pointer that sweeps across the entries on every access. Right? You move it to the thing you just accessed, and then you evict one of the other guys and not the guy you just accessed. Right? So that's a simple way to approximate this. So there's a whole load of different strategies you can try. LRU, but to give you the mindset, what's important, you're trying to exploit temporal locality, so try and keep things in that you've touched recently, and prefer to kick out things that you haven't touched in a while, right? That's exploiting temporal locality. Okay, so how good does all this stuff work in practice? Well, here's some data. I forget exactly which benchmark mix. I think this is a suite called SpecInt 2000, which is a relatively old workload for computers. So somebody took that code, compiled it for a given machine, I believe it was a MIPS, ran it with different cache configurations, and plotted the miss rate. So for these different cache sizes, what are the miss rates you actually get running reasonably realistic programs? And so what we're seeing on this axis are different associativities, 1-way, 2-way, 4-way, 8-way. On this axis, the miss rate. And the different lines are for different total cache capacity. So remember, you can take the same capacity and divide it up between sets and ways, as we talked about earlier. So let's just take a look at this case. So with a 1 kilobyte cache, that's a pretty small cache, 1 kilobyte, right? If it's direct mapped, you're getting like a 13% or so miss rate. That might seem bad, but if your class is half full, you'd say, wow, I'm getting an 87% hit rate, right? So quite often I'm getting a hit, right? Even with a 1K direct map cache. That's very, very tiny cache, very primitive organization. I'm still getting like nearly 90% hit rate. And that's pretty amazing. That's the power of locality. It's kind of there in the programs. Now, as you increase the capacity of the cache, things get better. So going up for 2 kilobytes, 4 kilobytes, 8 kilobytes, 16 kilobytes, 32 kilobytes, 64 kilobytes, 128 kilobytes. But notice something happens here. Like, I've doubled the cache. Did my miss rate go down by a factor of 2? No, much less, right? So I doubled the cache, but I didn't halve the number of misses. Why is that? Why should you expect it not to go down by a factor of 2? But much less than that. What do caches rely on? What are all memory? Yep.
The principles of locality, we're not using randomly what's in there. So.
Yeah, exactly. It's the principle of locality, right? So if caches work at all, that should tell you, well, obviously, the point of using the cache is a small memory. I can get almost all the hits of this huge big memory, right? So if the big memory, by definition, has a 100% hit rate, and I use a 1K cache, and I get nearly 90% hit rate, why would you expect adding, most of the hits are going to be in that initial 1K. Adding another one's going to help a bit, but you've already captured most of the locality just in that initial 1K cache. So the principle of locality tells you that don't expect doubling the cache size to halve your miss rate, right? Most of the accesses are clustered around some common addresses. Now, there is some benefit, and as you go down, you can see there's benefit. But notice I'm increasing the cache by factors of 2 here. I'm getting just a % or 2 increase, drop in miss rate, right? And that's basically the principle of locality. Even a tiny cache captures a lot of the locality, right? So making it progressively bigger doesn't help that much. Now, how about that's just going down this line vertically between the lines, right? Changing capacity. How about changing associativity? Let's just look at this guy, the 1 kilobyte. So going from one-way associative to 2-way associative. Now remember, we kept the capacity fixed. These are 2 1 kilobyte caches. One is direct mapped, one is 2-way. There's also an appreciable drop in miss rate. It's not quite as much as doubling the cache size, but it's almost as good. Right? So doubling the associativity in that case almost gives you as much benefit as doubling the cache capacity. Right? In terms of area, doubling associativity is much cheaper than doubling the capacity. Right? Though there's a cost in access time. Right? And one thing you'll notice is the lines are steeper for the smaller caches, and they start to level out as you get to bigger caches. Now, why is that? Why is associativity less helpful when you have bigger caches? Why does it give less of a percentage? Why is the slope shallower as you go to larger caches? Why does associativity help less? Yep. Right, so there's less cases where two things are mapped to the same set. Basically, remember, the reason you add associativity is to avoid those conflicts where two things try to map to the same set. As you get bigger and bigger and bigger caches, there are more sets anyway, so the probability of two things landing in the same set just goes down, right? So the number of ways in which you can get bad collisions just decreases as you increase that. So associativity matters less as you get to larger and larger cache sizes. Okay, so this is sort of data that backs up these ideas of locality. Okay, a bit of a minutes trivia. Just to repeat last time, the project's due on Sunday. We'll penalize those who ask but don't search on Piazza. We know who you are. The Guerrilla sections are starting this weekend, I believe, from 3 to 5 was the chosen slot on Saturday. So just check on Piazza for those times. I think that the poll is closed. We decided on some times. And remember, in the Guerrilla sections, we're going to focus on the lecture and exam material and not on the projects. Okay? Okay, let's take a 2-minute break. Okay, let's start up again. So, in trying to understand caches, architects came up with this idea called the 3 Cs. And actually, it was a fellow named Mark Hill. He was a graduate student here at Berkeley, and now is a professor at Wisconsin. And he came up with this analysis called the 3 Cs. And the 3 Cs are different categories of misses. So understanding how to improve performance, the first thing you got to do is analyze where the miss is coming from in the first place. So the first category we call compulsory misses. This is the first C. And this is relatively easy to understand. When you start running a program, if you haven't seen an address before, the cache doesn't know you're interested in it. And so until the first time you see an address, there's nothing the cache can do. It's going to take a compulsory miss. It has to miss. It hasn't seen that address before. It has to go to memory to put it in the cache. So those are sometimes called cold start, like you power your machine on, the cache is empty, you start running code. Every address, the first time you touch it, that's a compulsory miss. Now, it's kind of pretty much difficult to avoid having a compulsory miss, hence the name. But for long-running programs, it really has a small effect, right? So the things you access a lot, you do access a lot, and the cost of the initial access is amortized over all the other accesses you make to it. So compulsory misses are usually a small effect on performance. The second C is capacity misses. And these are misses you get because the cache simply does not have enough capacity to hold all the data you're working on right now. So if you have a program that's striding through an array that's a megabyte in size and your cache is 4 kilobytes, and you're repeatedly stepping through the whole megabyte array, there's just no way it'll fit in your cache, and so you'll get lots and lots of capacity misses. They just cannot fit all that data in the cache at the same time, the data you're working on, and so those are going to be called capacity misses. And the obvious way to solve those is make your cache bigger. Give it more capacity. However, that will then slow the access time, right? So that's the trade-off. But the second C is capacity. And the third C is collisions. So collision misses are misses that occur even though you have enough capacity in the cache. The addresses you want to hold in the cache are mapping to the same set in a way that you get conflicts, right? So those are called conflict misses. So these are the different 3 Cs: compulsory, capacity, and conflict. So one way to avoid conflicts is actually just make your cache bigger, like we just discussed. If you make your cache have higher capacity, that will tend to also reduce conflict misses because there's less probability of 2 things mapping to the same entry in the cache. You should all be familiar with hash tables, and you can think of a cache as kind of a hardware hash table, right? So the bigger you make it, the less chance there is of a conflict. The other way you solve conflict misses is by increasing the associativity in your cache, and so there are more ways in each set. So any conflicting addresses, you can actually hold more of them at the same time in the cache, right? So compulsory, cold start misses, nothing you do about them, first time you see the address. Capacity misses are misses that are because your cache is just too small to hold the data you're touching repeatedly. Conflict misses is where your cache is big enough, but because of the restrictions in placement, you're getting conflict misses that cause you to kick things out. Now, to measure these, you cannot actually online in your hardware detect which one of these it is. What you have to do is take your program, run it in a simulator, and do some analysis to tell you what category each miss is in. And the way you do this is, for compulsory misses, in your simulator, this is easy to do, make your cache be infinitely big and fully associative, right? So it's the best cache you can have, so it never misses, it never kicks anything out, and everything can live there in the same time, and just see how many misses you get, right? So that'll tell you the compulsory misses. Infinite size cache, fully associative, impossible to build, but easy to simulate, right? So just model that, and that'll count those misses. That's the compulsory misses in your program, okay? Capacity misses. Now change your cache size down from infinity a bit, make it finite in some powers of 2. So change it in powers of 2 and count misses in each reduction in size, right? So from 16 meg, 8 meg, 4 meg, for example. And those extra misses you get on top of the compulsory misses are capacity misses at each of those sizes, right? So first do the compulsory misses, then make your cache size finite and rerun the trace and see how many additional misses you get from that reduced capacity. And I'll tell you the capacity misses at each of those sizes. Okay? Finally, for the conflict misses, change your finite size cache to not be fully associative, but instead have some restricted associativity. Say, for example, 16-way, 8-way, 4-way, 2-way, 1-way. And then the additional misses you get on top of what you had for that same capacity, those are your conflict misses. Okay? So by repeatedly running the program multiple times in a simulator with different cache organizations, some of which you cannot really build, you can categorize where the misses are coming from in your program. Right? This is a useful thing to do to understand cache behavior. Because the other thing to realize is cache behavior doesn't just depend on the cache hardware. It mostly depends on the programs you run on it. Yep, question?
So is capacity like if two memory accesses are too far away in the main memory?
No, so capacity misses are, so to measure capacity misses, you have a finite size cache, but it's fully associative. So it doesn't matter what the memory addresses are that you're trying to touch. If they can both fit capacity-wise in the cache, it doesn't matter what address they're at. Right? So capacity has nothing to do with how far apart the addresses are, because in the cache, any address can live in the cache. And any two addresses can coexist in this middle case where you have a fully associative cache with some finite cache size. Okay, any more questions about this? So,
Why does increasing the block size help with compulsory?
yeah, so this is a good question. How can you do anything about compulsory misses? Right, it seems like if I haven't seen this address before, how can I get a hit on it? What happens if you make the block size bigger than one word? Say again?
You take in more data.
Right. So if you make the block size is bigger than one word, you bring in some data the processor never asked for. Right? So say I'm stepping through an array one at a time, A0, A1, A2, A3, A4, and my line size is 4 words. First time I touch the array, I get a compulsory miss on A0. But I don't just bring in A0, I actually bring in the whole line, which has 4 words on it. And lo and behold, A1, A2, and A3, I get hits on them, even though I never asked for those addresses before. The cache brought them in for me without me demanding them. And so that's how you can actually avoid a compulsory miss. So it's not really compulsory, but it's really a code stop. The first time I seen that. So those long cache lines help compulsory misses by prefetching other data you never asked for. And by the principle of spatial locality, there's some hope that other data you brought in you'll actually use. Because if I touch one location of the memory, it's more likely I'll touch neighboring locations than anything else. Right, so that's how they help. Okay. So looking at data, so now you've got a way of generating this data. You can now do the analysis and run it on some programs. And this was for the Spec 2000 integer and floating point benchmarks. So what the graph is showing is the x-axis is the cache size. So in powers of 2 from 4K to 1 megabyte. And the y-axis is the miss rate. And the different colors represent the different sources of those misses. So conflict, capacity, compulsory. Right? And these different regions are different associativities. So for one thing, for these long-running real benchmarks, the compulsory misses are basically negligible. They don't really matter. And so they don't even show up on this graph. They're kind of mostly irrelevant. Now, capacity misses this bottom line, and they're mostly a function of cache size. As you expect, as I increase the capacity, the miss rate goes down. Now, one thing you might notice, this is averaged across all these programs, but if you look at one program at a time, what you'll see is that miss rate versus capacity curve, it won't just go down in some smooth way. It'll have like steps and plateaus. Right? Kind of do this. Any idea what's going on? Why does increasing the capacity not help until suddenly it helps a bit? Then it doesn't help, and suddenly it helps a bit. Any idea what's going on in programs to cause that effect? You see it a little bit here. It kind of drops, then it stays flat, then it drops again, then it stays flat. Why are there those plateaus in Capacity versus miss rate. What do you think is going on in the program to cause that? The back? Right, exactly. So any given program, there's some important data structures in that program. And so you have an array. A simple example is an array that you touch every element in the array. Say the array's 16 kilobytes in size, and you repeatedly go over this. If your capacity is less than that, you're going to pretty much miss the whole time touching this array. If your capacity is greater than that, you're pretty much going to hit all the time touching that array. So as soon as some data structure completely fits in the cache, all of a sudden you get a significant drop in miss rate. You've captured what we call a working set of the program. And usually these happen at different scales. The same program will have different phases or different data structures of different sizes. And so that's why they have multiple of these plateaus. There's one and then another of your important data structures actually all fit in the cache. So there's this very nonlinear effect as you capture important data structures inside the cache. Okay, that's why this doesn't just drop smoothly. The other thing to notice here is the conflict portion. So the conflicts are what the difference from having one-way to two-way to four-way. As you notice, getting past four-way associative, there's sort of diminishing returns. You don't really see much. You got rid of most of the conflict misses basically at 2 to 4-way. And there's diminishing returns past that in general for most programs. But notice also that conflict misses are decreasing in sort of an absolute value as you increase the capacity. And again, that's what you would expect. The bigger the cache, the less likely you're getting conflict misses anyway. They tend to spread out over the larger number of sets, and so there's less chance for conflict misses. Okay, so this analysis is useful, especially when you look at a single program. You get a good sense of how what I can do about that given program. Now, one thing architects like to do is, improving cache performance. And if you look at the AMAP formula, this is very clear what you have to do to improve cache performance, right? Reduce the time for a hit. Make the cache smaller would be an example, right? Because hit time is an important component of the AMAP. Second thing you might do to improve cache performance, reduce the miss rate. That's another important component. How would you do that? You make the cache bigger. Reduce the miss penalty. How are you going to do that? Well, one way we'll talk about next time is using multiple levels of cache. So if caching works from just one level, from processor to big main memory, instead of going directly from the misses from the cache to main memory, you can put another cache in the middle there. We'll talk about that next time. Right? But basically, you have to find some way of reducing these three components to reduce the cache miss rate, to reduce the memory access time, and that'll improve cache performance. So we'll talk about some of the ways people do. So what's the impact? So notice we had bigger cache and smaller cache here. Well, let's look at what is the impact of a larger cache on average memory access time. Well, first of all, we know it reduces misses. So what kind of misses? Bigger cache reduces what kind of misses? Capacity. What else? Conflicts, right? Capacity and conflicts. Because it's less likely two things map to the same place. However, the downside is you have a longer access time, so your hit time is going to go up. Bigger memory is a slower memory. If it gets too big, you need a second stage in your pipeline. It may take 2 clock cycles to access the memory instead of 1, and that'll have an impact on your performance. Or you might have to make the clock cycle time longer, which will also impact your clock frequency, and that'll also make it slower. So if you're thinking about sizing the cache, what the simple thing to do for simple pipelines is make it big enough, as big as you can, without crossing the cycle time you're shooting for, right? So make it as big as you can without growing the critical path of your processor past the limit. Because actually hit time is one of the most important things, because most of the time you're getting hits in a good design, right? So don't grow the hit time too much. And architects spend a lot, as you see, this is not simple, there's a trade-off. Architects spend a lot of time optimizing this stuff. Okay, so let's have you play architect. Just quickly, I'm going to do these pretty quickly. So we just do a few polls to see if you get this. We kind of talked through most of these already. So there's 3 questions here, sub-questions. For each one, there's A, B, or C choices, right, for a fixed total cache capacity and associativity. So I'm fixing capacity and I'm fixing associativity. The only variable is how big the blocks are. So total capacity is the same, but I'm making the blocks bigger. What effect will that have on these three things, compulsory capacity and conflict misses? Your choices are A, decrease, B, unchanged, C, increase. We're going to do the compulsory first. So what impact does growing the block size have on compulsory misses? Cache capacity is the same, associativity is the same. Compulsory misses, decrease, unchanged, increase. Just get 30 seconds for these. Okay, a lot of confusion. All right, let's take a look. So, capacity is fixed. Associativity is fixed. So if you make the blocks longer, right, there's going to be fewer of them in the cache, right? The associativity is going to stay the same. But for compulsory misses, remember, on general, you expect it to decrease, right? Because there is spatial locality. If you bring in more data on every access, you're bringing in stuff you didn't ask for, and that should, if there's spatial locality, that should bring down your compulsory misses. The right answer would be A. Okay, that was the winner, but it should actually go down a bit, right? So although they are called compulsory, they're not actually compulsory, right? There is ways of reducing compulsory misses. Longer cache lines is one of them. Okay, second one, same setup, but now we're asking about capacity misses. What do longer cache lines do with a fixed capacity and fixed associativity? If you have longer blocks, what effect do they have on capacity misses? Okay. All right, so we have a clear winner, but people worry about these two as well. Okay, let's look at this. Well, the simple answer and the correct one to put on an exam is it will leave it unchanged, right? If I increase the block size, keep the capacity the same, the capacity misses should really be unchanged. In practice, you might find there is a strictly on capacity misses, there won't be a change. But for things that are limited by capacity, you might get a slight improvement, because if you're getting capacity misses, you have to reload stuff. And when you reload it, the longer blocks may help you cut the miss rate. But the right answer for an exam is the capacity misses are unchanged. Right? In practice, it might actually go down, but the right answer is unchanged. Finally, conflict misses. So fixed capacity, fixed associativity, but I'm going to increase the block size. What's the effect going to be on conflict misses? A, B, or C? Decrease, unchanged, increase. Okay, so, clear winner is increase, but some people unsure here. So let's go back, look at this. So the capacity is fixed, the associativity is fixed. If you make the blocks longer, you're going to have fewer blocks, right? If you have fewer blocks, conflicts are going to increase. There's fewer places to put stuff with the same associativity, right? So there's going to be fewer sets, right? So any way to get longer blocks with fixed capacity, fixed associativity, is to reduce the number of sets, right? And so you're likely to get more conflicts. So it should increase in that case. Okay, this one you can do by yourselves. So the name of the game is reduce AMAT, reduce the hit time, reduce the miss rate, reduce the miss penalty. You have to balance all these parameters. So next time we'll talk about more advanced stuff in caches.